All right, we are beginning a whole new unit, logs and their properties. And so we're going to start off with lesson 14-1, exponential data. And so in the very beginning of the year, we had arithmetic and geometric sequences and series. I apologize for my spelling here. Let me fix this. This is geometric. All right, so arithmetic were linear functions, right? They're increasing or decreasing by a constant difference. D, geometric, they're going to look like exponential growth or decay, which we've talked about before. And remember, we're multiplying by a common ratio. And so if it's growing, then that common ratio would be greater than 1. And if that is exponential decay, then it would be that the ratio is a number between 0 and 1. So again, our common ratio will tell us if we have exponential growth or exponential decay. Okay, so the learning targets today are to complete tables and plot points for exponential data. We're going to write and graph an exponential function for a given context. And then we're going to find the domain and range of an exponential function. So off to the side, we have some vocab. Magnitude refers to the size of something or the amount. It's often used in discussing the size of earthquakes or the brightness of stars. And then seismic waves are created by earthquakes, volcanoes, or other vibrations. All right, so we all know what an earthquake is, but in 1935, Charles F. Richter developed the Richter magnitude test scale to compare the size of earthquakes. The Richter scale is based on the amplitude of seismic waves recorded on a seismograph at various locations after being adjusted for the distance from the epicenter to the earthquake, or of the earthquake. Richter assigned a magnitude of 0 to an earthquake whose amplitude is a 1 micron. According to the Richter scale, a magnitude 1 earthquake causes 10 times the ground motion of a magnitude 0. And a magnitude 2 causes 10 times that of a magnitude 1, and so on. This pattern continues. All right, so let's go back and summarize. So a magnitude 0 earthquake is called 1 micron. And then according to the Richter scale, a magnitude 1 earthquake causes 10 times the ground motion of a magnitude 0 earthquake. And a magnitude 2 earthquake causes 10 times the ground motion of a magnitude 1 earthquake. So right now they're telling us that our common ratio R is 10, right? Each time it's 10 times as large. That's what we're multiplying by. Reason quantitatively, how does the ground motion caused by the earthquakes of these magnitudes compare? So please, with your group, go ahead and discuss item 1A, B, and C, and then we'll come back together. All right, so a magnitude 5 compared to magnitude 4, there's one difference in magnitude. So the difference in magnitude is 1. So that implies that it is 10 times stronger, or the ground motion is 10 times larger. Okay, from a magnitude 4 to a magnitude 10, the difference in magnitude it's a 1 versus a 4, that's a 3, a difference of 3. And so that tells me that it's 10 times 10 times 10 times stronger. Or you could say that's 10 to the third times stronger. Or you could say that that's 1,000 times stronger. And then a magnitude 4 versus a magnitude 0, the difference in magnitude is 4. So it will be 10 times 10 times 10 times 10 times stronger, which is 10 to the 4th times stronger, which is 10,000 times stronger. All right, please read the list below. It talks about the typical effects of earthquakes at varying magnitudes. If there's any vocab that you need to go over with your group, please do that. And then we're going to move on to the next page. So complete the table to show how many times greater as the ground motion is when caused by each earthquake compared to a magnitude 0. So recall that our growth factor, right, or our common ratio is 10. So we're multiplying by 10 each time. So please go ahead and fill in your chart. So hopefully your chart was, the next one would be 1,000, then 10,000, and so on. So I'm going to fill in my chart. Please verify that you have the same values in your chart. Okay, so we're at 10, 100, 1,000, 10,000, 100,000, 1 million, 10 million, 100 million, 1 billion, and 10 billion. All right, in parts A through C below, you'll graph the data from item 2. Let the horizontal axis, so horizontal is the x-axis. The x-axis is going to represent the magnitude, and the y-axis, the vertical axis, is the ground motion, or the strength of the earthquake. All right, you could also use a graphing calculator, it says. So it says, alternatively, you can use technology to perform an exponential regression. We'll talk about that later. Right now it says to plot the data using this grid. So they want us to use a grid that's from -10 to 10 on the x-axis and from -10 to 10 on the y-axis, and go ahead and graph your data. So what I'd like you to do is try to graph this data on this axis and then describe if it's a good choice or not. So please go ahead and do that with your group. So what I see is that I can only get one piece of data on here. The point 1, 10 is the only data point that will fit. If I go to 2, 100, it'll be way up there off the chart. And so this is not a good choice. Only one data point fits on this graph. All right, and I'd like you to do the same thing for B. This time you're using from -10 to 100 for X and -10 to 100 for Y. Go ahead and with your group, go ahead and attempt to graph your data and then decide if it's a good choice. So what I see is that my x-axis is going to be really crammed together. It's really hard to see. There's 10, right? So 1, 10 is right about there, very close to the axis. And then 2, 100 will fit. And so I can't really see any more data. So I would say this is not a good choice. Only 2 points will fit. On the graph. So what I would want to do is I would want to definitely spread out my y-axis, or x-axis, excuse me. I would want this to be maybe only up to like 5 or 10. And on the y-axis, I'd want this to go a lot higher. So that's what we're going to do on the next one. It says you can adjust your scales to see this easier. So I'm going to, remember, be graphing these data points versus these data points. I think that if I graph the first few, maybe the first 5, I would be able to see what's happening in the graph, especially you can see how quickly the exponential functions grow. So to put all of these x values and y values wouldn't really be necessary, but I need to get a good 4 or 5 on there so I can see what's happening. So I'm going to select for my x-axis, remember this is my magnitude, I'm going to count by ones. And for my y-axis, and remember this is going to be the ground motion, I'm going to count in thousands. So the first will be 1,000, and then 2,000, 3,000, 4,000, 5,000, 6,000, and so on. And that will let me get to at least these first 4 points. Okay, so I'm going to go ahead and graph my first point. My first point is 1, 10. 1, 10 would be really, remember these are in thousands, it'd be really close to the axis. And then 2, 100, just a bit up. 3, 1,000, 3, 1,000 would be right here. 4, 10,000 would be right there. And then 5, 100,000 will be way off my graph. But these 4 points can help me to see a little bit more clearly my function growth. So we have a nice, smooth, continuous function growing exponentially. All right, so it says to plot the data, we did. Label at the scale and the axes, we did. And then draw the function that fits the plotted data, we did. When we connect those lines, we're drawing the function. All right, it says to write a function g of x for the ground motion. So to write a function, you look at first your growth factor, r, right? Our growth rate is 10. It's being multiplied by 10 each time. And exponential functions, right, are always written as something like with geometric functions, we had in a geometric, we had a times b to the x. Okay, and so a was our initial, like this was a1, and b is our growth rate. So that's just a refresher from back when we did exponential functions. So g of x equals a, well, our initial, remember our initial, we have to go back to the very beginning. And it says our initial magnitude is 1, right? So a is going to be 1, and our growth rate, r, is 10. And so our function would be 1 times 10 to the x power. We don't really need to write multiplying by 1, so I'm going to rewrite this. G of x equals 10 to the x power. Now, whenever you write a function, you should always confirm that when you plug in values for x, right, x is our magnitude, that we get out the proper values for y. So I'm going to verify that here. Remember, we're back on page 192. My function that I wrote was g of x equals 10 to the x power. If I plug in 1 for my magnitude, I get g of x equals 10 to the first, which is 10. That's correct. I want to verify this for at least a few x values. 10 to the second, which is 100, when x is 2, y is 100. G of x is 10 to the third, right? 10 to the third is 1,000, so 3, 1,000. So these are correct. So my x values and my y value, corresponding y values are correct. And then we should also check for our initial value. If we have 10 to the 0, right? Anything raised to the 0 power is 1, and that was my initial value. So always confirm when you write a function that you have the correct function. All right, so in your groups, please, you're going to do the check your understanding, and then we'll come back together and discuss. So what is the domain of the function? Remember, domain is your x values. And so obviously we cannot have a magnitude that's negative. And so our domain for our x values is going to be from 0 up to 10. And our range is, we didn't talk about the range. It just wants us the domain. So the domain would be from 0 to 10, right? We don't have any values outside of that. And then it says that is the function continuous? So continuous means that that there's no gaps or holes, right? Or asymptotes of the graph. Yes, it's continuous. And the reason is that there are no points of discontinuity. There are no points of discontinuity. Between this domain. Okay. Use the graph from item 3C to estimate how many times greater the ground motion of a 3.5 is to the magnitude of a 0 earthquake. All right, so we know that at 0, we would have a magnitude at a magnitude 0, we'd have a ground motion of 1 micron. And at 3.5, which is roughly like right here, I'm going to estimate that it's somewhere between, at a magnitude 3.5, it looks like it's about 3,000, maybe 3,200. So that's a good estimate. And if you were to use a graphing tool like GeoGebra or Desmos, you would find that the actual value is 3,162. Okay, so moving on to 6A and 6B. It says in item 3, the data were plotted so that the ground motion caused by the earthquake was a function of the magnitude of the earthquake. Please, with your group, can you read 6A and 6B together? All right, so 6A, is the ground motion a result of the magnitude of the earthquake, or is the magnitude of the earthquake a result of the ground motion? So I want you to think about that, and then tell me which one do you think is a result of the other. And so we would say the magnitude is a result of the ground motion. And the reason that the magnitude is a result of the ground motion is that we can't assign the magnitude until we see how much the ground moves. So you can't, or you don't, right, assign the magnitude until we see how much ground motion there is. Okay, so what I said is that you can't assign magnitude until we see how much ground motion occurs. And so because the magnitude depends on the ground motion, the next question says, based on your answer to part A, would you choose ground motion or magnitude as the independent variable of the function? And then which one would be the dependent? So we know the magnitude depends on the ground motion. So the magnitude is the dependent variable. So dependent would be magnitude, and independent would be the ground motion. And so when we graph these kinds of things, the independent variable, these are always our x values, and the dependent variable is actually the y values. So remember, we usually choose our values for x and plug them in to get y. And that's exactly what we would do here, right? We would choose values for x. Oh, we had a we had this much motion. That means the earthquake was this magnitude. And so we would plug in our x values, our ground motion, to find out our magnitude. And so they want us to regraph our graph. And so what's going to happen is that we're going to now graph on this axis. This will be our ground motion. And on this axis, this will be our magnitude. And so going back to our table, we need to graph, I'm going to graph just those first few points. So we're going to graph counting by 1,000s again. So this is going to be 1,000, 2,000, 3,000, 4,000, 5,000, and 6,000, and so on. And then our magnitude, this will be 1, 2, well, actually, I think I'll put 1 right here, 2, 3, and 4, because I know I'm not going to be able to get all those values on there. All right, so when my ground motion is 10, my magnitude is 1, so that's going to be like right here, really close to the axis. And then when my magnitude is 100, which is about right here, when my ground motion is 100, my magnitude is 2. When my ground motion is 1,000, my magnitude is 3. And then when my magnitude is 10,000, which is way over here, my magnitude is 4. And so my graph would be doing something like this. All right, so my original graph, looked something like this. And now my inverse graph looks something like this, right? Okay. And so it says, let the function you graphed in item 6C be m of x. So y equals m of x, where m is the magnitude of an earthquake for which there is x times as much ground motion. Identify a reasonable domain and range for the function g of x. So a reasonable domain and range for the function g of x, remember g of x is the original function, is that we could have a magnitude 0 up to a magnitude 10. So from 0 to 10. And the range of our function would go from 1 to like 10 billion. So 1 comma 10 billion. And the range of this function, right, is actually coming from the magnitude from 0 to 10. And the domain is from 1 to 10 million. 10 billion. And so what we see is that these are actually inverse functions. If you recall, inverse functions, the domain of f of x is the range of f inverse x, and vice versa. And that is exactly what happens here. The domain of our original function is the range of the new function, the inverse function. And then the range of the inverse of the original function is the domain of the inverse. All right, in terms of the situation, describe the meaning of the ordered pairs on the graphs. And so in your group, could you please do that? Please describe the meaning of each of those points. So this would be your x comma y. On g of x, this would be the Richter magnitude. And this would be the ground motion compared to magnitude 0. And in m of x, this is our ground motion compared to magnitude 0. And this is our Richter magnitude. All right, let's move on to the next page, page 195. So page 195, it says a portion of the graphs of g of x and m of x are shown on the same set of axes. Describe any patterns you observe. So please, with your group, can you describe any patterns that you observe? So something that I observed is that there's symmetry across the line y equals x. Also, I noticed that the point 1, 0, 0, or I think that's actually 1, 1. Yeah, it's 1, 1. The point 1, 1 is the same over here, 1, 1, right? They're reflected across that line. Also, this point at 10 comma 1. Oh, that's 10. That is 1 0, and this is 0 1. My bad. And then right here, this point, 10 comma 1 is the same as 1 comma 10. So my x's and y values switched. If you noticed anything else, I don't think I really noticed anything else about this graph, but that's what I noticed. All right, with your group, can you please describe how you chose the scale of the graph that you drew in item 6C? How do you choose the scale of the graph? And then what is the relationship between the functions? All right, so I would choose my scale based off of the reversed axes from the previous graph from 3C. So I would reverse the axes, I should say, from number 3, part C. And what is the relationship? I already talked about it. These are inverse functions. All right, so they're giving us a table here, and it says the table shows the approximate energy released from an underground earthquake of different magnitudes in terms of the explosive force of the amount of TNT. So TNT is dynamite. And so the magnitudes versus the energy created are listed here. Let's move on to the question. It says determine an appropriate subset of the data and a scale for the graph. Plot the data and label the axes and the scales. Draw a smooth curve through the points. So that is what you're going to do in your groups. So this is going to be our magnitude. And this is going to be our energy in kilograms. So my magnitude is going to be 1, 2, 3, 4, 5, 6. And my energy, I'm going to go ahead and count by 50,000s. So 50,000, and then 100,000, and so on. 150, 200, 250, 300, 350, 400, 450, and 500. So let me just make sure I didn't skip any. 51, 52, 53, 54. Yeah, okay. 51, 52, 50. Oh, I'm off a little bit, but that's okay. All right, so the first one is at 1 comma, just to go back to our chart. Right, the first value is at 1 and almost non-existent. So it's going to be super, super close to the axes. The next one is 2 comma 15, which again is really close to the axis. And then 3 comma 480, still super close. You can hardly see the difference between these. And then at 4, 15,000 would go up a little bit. 5, 480. So that is huge, right? 480 is like right here. So 5 comma 180 is right there. And so our graph is going to be very, very sharply increasing. And we're going to draw a nice smooth curve to represent it. It says use a graphing calculator to perform an exponential regression and write a function. So you won't have a graphing calculator, but you can do this on Desmos. So I'll show you how to do it on my graphing calculator, and then on Desmos I'll show you how to do that separately. But in your in Desmos, it's pretty much the same thing. You want to create a set of values. So you're going to go you're going to write your order pairs in here. So what we're going to do is we're going to graph in the our points. So my x values, my magnitudes are going to go in list 1, and then my y values are going to go in list 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then my y values are going to be 0.048, 15, and so on. So 0.048, 15, 480, 15,000, 480,000. Oh, I think I put one too many zeros. Let me try that one more time. Oh, I have one too few zeros, sorry. 15, 1, 2, 3, 4, 5, 6. And then 480, and then 1, 2, 3, 4, 5, 6. And 480, 1, 2, 3, 4. Okay, so what your graphing calculator can do is something called as a exponential regression. And it's right here under calc. Of course, I would have to show you how to do a exponential regression in Desmos, but right here is exponential regression, and you tell it which two lists to use. And I'm going to say store it in nope. Let me do that again. There we go. And so you notice that this exponential regression equation is the one that I was talking about. Y equals AB to the x power. Y equals AB up to the x power. And it says that A is 0.006 and B equals 35.84. And so our exponential regression equation, it says round each value to the nearest thousandth. So I think I need one more place value for B. So we're going to just rewrite this as e to the x, right? Here's my function. E to the x equals A, 0.006 times B, 35.842 up to the x power. All right, now you cannot do these kind of regressions without a calculator, but they're kind of cool once you know that you can use your calculator to, without this kind of a calculator, I should say, once you know that you can use this kind of a calculator to create your exponential regression equation, I mean, it's pretty cool. And you can do the same thing in Desmos. All right, what is a reasonable domain of the function in item 10b? Use interval notation. So remember, domain is your x values. Magnitude can be from 0 to 10. And that is interval notation. And then refer to your function in item 10b about how many times more energy is released when the magnitude of the earthquake increases by 1. And so we see that that actually is our growth factor, right, B, which is about 35.8 times more energy. And so it's about, if we're going to round to the nearest, it would be about 36 times greater. All right, I hope that you enjoyed the notes and do your homework. I can't emphasize this enough. If you're not doing the homework, you will not understand the material, which will mean that you will not understand the quizzes and tests. You must keep up on your homework. That's all I have for today, guys.